This is topic number 3, operations with radicals and solving by taking the square root. Now recall that taking the square root reverses squaring a number. So our goal when we are trying to find factors of 12 to use only perfect squares. So I could use 6 and 2, but 6 isn't a perfect square. So I'm going to use 4 and 3, the factors 4 and 3, because 4 is a perfect square. And we're going to try and find 2 of a kind. 4 times 3 gives me 12. But I do not yet find 2 of a kind. If I continue to break down 4, that's 2 times 2 times 3. Now I've found 2 of a kind. Because remember, taking the square root reverses squaring a number. So if I squared 2, that's 2 times 2, and I'm reversing that. So I'm going to remove the 2, and I'm going to bring it out in front. Whatever factors remain underneath the radical, they remain underneath the radical because you couldn't find 2 of a kind. So our final answer would be written 2 times the square root of 3. And in case you didn't know, when there is no number written right there in the index, there's an invisible 2. So you're trying to find 2 of a kind. Let's go to number 2. 45 times x squared. So my goal is to find factors that are perfect squares. 9 times 5 gives me 45. X times x gives me x squared. I've located the first 2 of a kind, but I know that 9 is a perfect square, so I'm going to continue to break that down. So if I break down 9, that's 3 times 5 times x times x. Now I've found my 2 of a kinds. There's a 2 of a kind. The x's are 2 of a kind. Remember, taking the square root is reversing squaring a number. So I'm going to remove one of the 3's. I'm going to remove one of the x's. The final answer will be written as 3 times x times the square root of 5. So if you have two of a kinds underneath the radical, when you remove them, you multiply them. So that's the same thing as 3 times x. Now this operation will be subtraction, and you're going to treat this just as you would if the square root of 5 were a variable, and you're going to combine like terms if you can. So here we have a square root of 5 minus a square root of 5. Now here's another invisible number. There's an invisible 1 right there. So we are going to subtract negative 2 minus 1, and the reason why we can is because the square root of 5 has this, it's the same number underneath the radical, so we can combine them just like we were combining like terms. So negative 3 minus 1 is negative 2 minus 1 is negative 3 times the square root of 5, and that's your final answer. So you can add or subtract radicals if the radicals have the same number inside of the radical. Number 4, addition. Now if you notice here, we have a square root of 6 and a square root of 24. Uh-oh, they're not the same. But if we try to find some 2 of a kinds, we might be able to simplify, and then we would be able to combine. So if I were to break down that 24, the factors would be 4 times 6. And I know that 4 is a perfect square. So I'm going to break it down just like we did in problem number 1. So negative 3 times the square root of 6 plus 2 times the square root of, well, 2 times 2 gives me my 4 times 6, and there you go. There's your 2 of a kind. So I'm going to reverse squaring a number by taking the square root. When you remove it, you're going to multiply by any number that is in front of the radical. So when I rewrite this, it's negative 3 times the square root of 6 plus 2 times the square root of 6. And I'm going to simplify the 2 times 2, and I get 4 times the square root of 6. Now we're ready to combine like terms. It just so happens that we now have terms that we can combine. The 6 and the 6 underneath the radical are the same. So now we can combine the term in front. Negative 3 plus 4 is 1. 1 times the square root of 6, but we don't need to write that invisible 1. We can just write the invisible 1 times the square root of 6. it means the same thing. Number 5. Looks like we have 3 terms that we're going to try to combine. I already noticed that this is a radical 5 and this is a radical 3, and they will not be able to combine. But if we break down this 45, I might be able to combine it with this radical 5 or this radical 3. So let's see what happens when we break this down. 3 times the square root of 5 minus 2 times the square root of 9 times 5 plus 2 times the square root of 3. I'm going to continue breaking down this 9. So 3 times the square root of 5 minus 2 times the square root of 3 times 5 plus 2 times the square root of 3. There is my 2 of a kind that I'm going to remove. 3 times the square root of 5 minus 2 times 3 times the square root of 5 plus 2 times the square root of 3. Now you notice that we have radicals that are the same, so we're going to be able to combine those. Let's simplify first. The 3 times the square root of 5 minus 6 times the square root of 5 plus 2 times the square root of 3. Now we're going to be able to combine those 2 terms because the square root of 5 is the same. So the square root of 3 minus 6. So you get negative 3 times the square root of 5 plus 2 times the square root of 3. And that is your final answer because you cannot combine the square root of 5 and the square root of 3. It would be like trying to combine an x and a y. Number 6. This is multiplication. So the operation is different than addition and subtraction. We are going to combine the 20 and the 15 underneath one radical. There's no point in multiplying these together because you're trying to find factors anyway. So then that just creates more work. So when the operation is multiplication, simply combine them underneath the radical. So 20 times 15, and our job is to break those down in factors to try and find as many 2 of a kinds as we can. Now I could use 2 times 10, but those aren't perfect squares. 4 times 5 is a perfect square. And I can also look ahead and see that I'm going to have a 5 as a factor of 15. So there's my first 2 of a kind that I locate. But I already know that 4 is a perfect square. But let's go ahead and break it down so you can actually see the 2 of a kind. 2 times 2, that's your 4, times 5 times 5 times 3. I'm going to go locate all of my 2 of a kinds. There's a 2 of a kind. There's a 2 of a kind. Now remember, taking the square root reverses squaring something. So I'm going to remove just 1 2. I'm just going to remove one of the 5s. Oops, and I forgot to put the 2 there, so we should have seen the original started with a 2. So when I remove a 2, I've got 2 of them in the front, and then the 5. So 5 times 2 is 10. 10 times 2 is 20. And then this 3 remains underneath the radical. That's the remaining factor. So the final answer should be written as 20 times the square root of 3. Number 7. We are going to distribute this radical. And when you distribute it, you're going to be multiplying it by the radical 5. So you're going to multiply the radical times the radical. So we're just going to combine these underneath one roof, just like we did over here, 20 times 15. So negative 2 times the square root of 2 times the square root of 5 is just 10. Plus the square root of 2 times the square root of 6 is 12. Now the reason why I multiplied that out is because I want to use the 4. I already know that 4 times 3 gives me 12 because we did that up here. So I want to do it just like I did in problem number 1. Negative 2 times 10 plus, since I've already solved radical 12 up here, I know that when I simplify it, it's 2 times the square root of 3. So I'm looking at my final answer, and I have to ask myself, can I combine these 2? And the only way I would be able to combine those 2 is if the square root of 10 and another square root of 10 over here, but it's not. We've got a square root of 10 and a square root of 3. We cannot combine those. Those are not like terms. So this is our final answer. Let's look at number 8. Number 8, we're going to have to FOIL. So some people prefer to use the box. So why don't we do that? I'm going to set up my binomial here, the square root of 3 minus 1, and I have to multiply the same binomial a second time. So the square root of 3 minus 1, so now we have our box to multiply. For those of you that prefer to FOIL, you can FOIL. The square root of 3 times the square root of 3 is the square root of 9. The square root of 9 is 3. So whenever you square a radical, the radical simply disappears. So that you're going to see that later. So the square root of 3 times the square root of 3 is simply 3. It just removes the radical because you're going to have 2 of a kind underneath the radical. The square root of 3 times negative 1 is negative root 3. Negative 3 times negative 1, negative root 3. Negative 1 times negative 1 is a positive 1. Let's combine like terms. I notice that I can add 3 plus 1. That's 4. Don't forget there's an invisible 1, negative 1 here. There's an invisible negative 1 there. So we can combine like terms by adding them. Negative 1 plus negative 1 is negative 2 times the square root of 3. And that is our final answer. Number 9. We have to write a fraction to include no radicals in the denominator. Not allowed. It's not considered completely simplified when you have a radical in the denominator. So in order to undo a radical, we're going to perform something similar here that forces us to get rid of the radical. So do you see here it's radical 3 times radical 3, and when you square a radical, the radical just disappears. That's what we're going to be doing here. So I'm going to multiply by a radical 3. Both in the numerator and the denominator. Now mathematically I can do this because this is a reduced value of 1. So I'm really just multiplying by the number 1. Anything divided by itself is just 1. So I'm not changing the value, I'm just simplifying it. This is called rationalizing the denominator. So I'm going to work this out so you can actually see the 2 of a kind. 4 times 3 times 3. So do you see how we have 2 of a kind under the radical? Remove it. It is undoing squaring something. So it's 4 times 3, and now we have 12, and we have eliminated the radical in the denominator. In the numerator, now let's simplify the numerator. So 2 times 5 times 3, 2 times the square root of 15. We are not done reducing. If I multiply 4 times 3, I get 12. And 2 and 12 can reduce. So 2 times the square root of 15 over 12, I can divide by 2. When I divide by 2, I get 1 times the square root of 15 over 6. You don't have to write the 1. That would be a case of another invisible number. You cannot reduce the 15 and the 6. Now, if you had the 15 perhaps on the outside, you would be able to reduce by the 3. But because this 15 is inside the radical, you are not allowed to reduce those two numbers. Here we have a binomial. And in this binomial, there's a radical. So we cannot have a radical in the denominator. So we're going to multiply it by a very similar binomial, but with a minus sign. And again, any number that has the same numerator and the denominator just reduces to 1. So we're not changing the value of this original fraction. We're simply rationalizing the denominator. So we can set up the box just like we did on number 8 to multiply these two. For the denominator, the numerator, we're just simply going to distribute this 3 to the binomial. So why don't we start with the numerator? I'm going to distribute this 3 to the 2 and the negative 4 times the square root of 3. So 3 times 2 gives me 6. 3 times negative 4 gives me negative 12 times the square root of 3. Now, I'm going to take these two binomials and I'm going to multiply it in the box below. If you want to FOIL this in your head, you can. 2 plus 4 times the square root of 3, 2 minus 4 times the square root of 3. And the reason why you want to have opposite signs is that's what helps you eliminate the radical, which is you're going to see in just a second. 2 times 2 is 4. 2 times negative 4 gives me negative 8 times the square root of 3. 2 times positive 4 gives me a positive 8 times the square root of 3. And then we have 4 times negative 4 is negative 16 times the square root of 3 times 3, but that just eliminates the radical. So it's going to be negative 16 times 3. When we combine like terms, that is negative 48. Negative 48 plus 4 is negative 44. We can combine these, and what you'll notice is that they eliminate positive 8, negative 8, like terms, so we can combine those. Those eliminate to a 0. So our denominator is a negative 44. I can reduce the 6, the negative 12, and the negative 44 because they all have a 2. It's all three of these terms are divisible by 2. All three must be divisible by the same number. You wouldn't be able to just reduce those two and leave this one alone. They all three have to be divisible. So if I divide this by 2, I get 3. If I divide the negative 12 by 2, I get negative 6. If I divide negative 44 by 2, I get negative 22. So as you can see here, the negative 6 and the negative 22 would be divisible by 2, but not the 3. So you are not allowed to reduce. Number 11. Solve each equation by taking square roots. Okay, well, the opposite of taking a square root, by taking square roots. The opposite of squaring a number is taking a square root. So that is how we're going to solve these. So I'm going to divide by 10 to get the n squared by itself. N squared equals 80. Now, when we are taking the square root of a perfect square, we must consider that the 2 of a kind could also be a negative number. So we always want to include both the positive and the possibility that it's a negative factor. So n equals plus or minus. Don't forget the plus and the minus. That's very important. I know that 8 times 10 gives me 80, but I don't see any 2 of a kinds yet. Let's keep breaking it down. N equals plus or minus 4 times 2 times 2 times 5. I see my first set of 2 of a kinds. So n equals plus or minus, but I'm going to continue breaking down that 4. That's 2 times 2. And then the other 2 times 2 times 5. I see 2 of a kinds. There's 2 of a kind. There's 2 of a kind. So I'm going to remove the first 2 and then the second 2, and I'm going to multiply those together. So n equals plus or minus 2 times the square root of 5, because that factor does not have a pairing with another 5 in there, so it remains underneath the radical. The final answer, n equals plus or minus 4 times the square root of 5. And 12. We want to get the r squared by itself. The first step would be to subtract 9. 4r squared equals 220. Now we're going to divide by 4 because this is 4 times r squared, and we're going to reduce that, or divide that. So r squared equals 55. To undo squaring a number, you take the square root of both sides. Don't forget, you must consider both the plus and the minus. You have to consider that there would be a negative times a negative, which could create a positive result. So it's important to always put the plus or minus. So r equals plus or minus the square root of 55. You cannot break the 55 down. It's 11 times 5. Both of those are prime numbers. That is your final answer. Number 13, solve each equation. So our variable is underneath the radical. We have to do opposite operations to solve for the variable. The first thing you want to do is remove any terms that are on the outside of this radical. Minus 2 is the only number on the outside of the radical, so we need to move that first. So now we have the square root of 5b plus 5 equals 5. So now we have the task of undoing this radical so that we can solve for b. Well, the opposite operation of taking the square root of a number is squaring it. That is the opposite operation of a radical, square rooting. So this eliminates the radical, and we now have 5b plus 5 equals 5 squared, which is 25. So now we can solve for b using opposite operations. Subtract the 5. 5b equals 20. Now divide by 5. b equals 4. Number 14. Here we have a variable on the left, a radical on the right. So I'm going to eliminate by reversing the operation of this radical so that I can access this inside the radical. So if I want to undo taking a square root, I square. And whatever you do to the left, you must do to the right. So n squared equals, now when you square a radical, the radical just disappears. Negative 56 plus 15n. I see a quadratic in here. I have an n squared. This looks to me like I could probably write this in standard form of a quadratic. This is what standard form looks like. ax squared plus bx plus c. That's standard form of a quadratic. I have this here, but I've got one on the left-hand side, part of it on the left, part of it on the right. So I'm going to move the right-hand side to the left-hand side because I want to keep this n squared a positive coefficient. This a value must remain positive. So I want this 1 n squared to remain a positive value. So I'm going to add the 56, I'm going to subtract the 15n, and I'm going to move them to the left-hand side. N squared minus 15n minus 56 equals 0. Now this hopefully looks familiar, and you might already be thinking, hey, we can do the diamond to factor and solve. So if I have n squared minus 15n minus 56, negative 56 goes on the top, negative 15 goes on the bottom, and in order to solve that diamond, oh, I'm sorry, we're adding the 56. Oopsie. Now, let's see. Negative 9, 8, and negative 7. Sorry, having issues there. All right. So now we have solved for our factors. So let's list the factors. N minus 8 times n minus 7 equals 0. So now that we have our intercept form, they want to know what are the actual intercepts because this is set to 0. So we're not going to just leave it in factored form. We actually have to solve for 0. So we're going to apply the zero product property. Some number minus 8 gives me 0. Well, that's got to be 8. Some number minus 7 gives me 0. Well, that's got to be 7. But you can also solve that algebraically by setting each of these equal to 0. N minus 8 equals 0, and solving by adding 8. So n equals 8. And you can also set this binomial equal to 0, that factor equal to 0, and solving by adding 7. So that's algebraically how you would do it. Now you have your notes for topic 3.